Yes. Thanks, John.
Great, perfect. So I am using my 2D mode, so I was worried I might get a little dizzy swiveling back and forth while doing this. So bear with me if there's any controls that are different and I look funny as I'm doing this, but we'll go ahead and get started. So yeah, my name is Jon Robertson. I manage the customer service department for the Teledyne Marine Acoustic Imaging Group for North and South America. We manage all the basically after sales support for three of the brands within the 26 brands in the Teledyne Marine Group, focusing on the different types of sonar systems that we manufacture. So I'm going to give kind of a general overview on the different types of sonars that we manufacture and try to focus on the autonomous vehicle applications and basically the imagery and product deliverables that our systems generate. So let's see. So just a brief overview of what we'll be going over. The different types of sonars we'll be talking about. 2D forward-looking imaging sonar, single beam echo sounders, multi-beam echo sounders, and a unique system that we manufacture is a 2D forward-looking sonar that also has the capability to do forward-looking 3D bathymetry imaging of the seabed in front of a vehicle. And then we'll take some time for questions at the end. So this is the product line that provides the 2D forward-looking real-time imaging sonar. And I'm not sure how familiar people are with sonar, so I kind of wanted to give some basic introduction of them as well. We manufacture a variety of systems for different types of applications, from high frequency, short range, high resolution imaging, and then low frequency systems that provide very long range, up to 300-400 meters range capability of imaging. So we basically have a large suite of systems that can really cater to a large variety of applications. So these sonars, this is an animated example of a sonar mounted on an ROV. As you can see, the animation of the field of view is pointing out in front of the vehicle, and the red beams are, there's not as many that are red beams that are actually in there, but it's just to indicate that there's hundreds of beams that are fixed mounted next to each other to build up a full field of view to provide real-time imagery, 2D imagery from that entire field of view. When we talk about the field of view, you have a horizontal field of view this way and in the yellow line, and then the vertical field of view. And this is essentially the design of all of the 2D systems. So it's kind of like a cone of area of coverage that we're insonifying and creating the imagery from that field of view. And then we have an animated comparison of a single ping, showing the imagery that you would get from a single ping in a still image. So we're imaging out in front of the ROV, and the data that we receive from the sonar is actually the point of view is from top down. So from an aerial point of view, we're looking at the area that's being insonified from the user interface. And I'll show a video example, I believe. Before going to the first video, just one of the things that is a big consideration in the quality and how we image the seabed or area of interest is the tilt angles and that we mount the sonar to. a lot of times remotely operated vehicles, ROVs, they're not autonomously controlled, and you are dynamically flying around looking at different areas of interest. So you would want to consider having a mechanical tilt on the sonar to provide different grazing angles to the seabed. When we talk about autonomous vehicles, you probably don't have that flexibility to be able to control the tilt angle besides what having the sonar fixed mounted in front of the vehicle or facing downward for obstacle avoidance. But that's something to consider when planning an operation. If you're focused on imaging the seabed from, for example, an AUV, you would want to make sure you have the sonar tilted in the correct angle based on what your goal is for imaging. If you're imaging the seabed, you might want to point it down more, and it'll also depend on your altitude from the seabed, how much tilt angle you want to introduce into that sonar image. So that brings us to our first video. I'm going to attempt to play on the screen to your right. So this is a video example of a 2D sonar that is mounted on a surface vessel in a ship terminal. So you see we have the full field of view providing a real-time image. A lot of times people will call this an acoustic camera. So we're using acoustics to provide a full real-time view of what's underwater. And as you can see, the seabed in front of the vessel, and then on the left-hand side is the seawall. If you look in the center, I don't know how well you guys can see the imagery, but in the center of this field of view, towards the end of the video, you can see and identify two tires that start to show up right there in the center. So you can see the type of resolution that you can get from these types of systems. Move on to the next example. So we have another video example. Let's see if I can go to the next video. So here's another example of a sonar mounted on a surface vessel imaging an area next to a bridge, and you can see the bridge is on pilings. And I like to compare the data to shining a flashlight in the dark also. If you shine a flashlight at a piling or a tree in the dark, there's a shadow behind the target, the tree, and that then you can really get a good idea of how the imagery is coming through. Play that again. There's on the left-hand side of this data set, there was a buried cable that this company was inspecting and looking for, and the high current was causing the seabed to erode away and caused some free spanning of this cable that you can see swaying in the water column on the left right there. And you can really see the shadow of that cable as well highlighted. So a unique way that autonomous vehicles use 2D sonar for navigation and obstacle avoidance is, instead of only having the array in the traditional horizontal field of view, some companies will rotate a sonar or have a second sonar rotated 90 degrees so that it can image and sonify an area or a target with the capability to measure the vertical height of structures. Now, that when you couple that with a control system of an AUV or a vehicle, that is underwater, then if the vehicle is control system is designed to be smart enough, it could calculate, how high, what's the vertical height of an obstacle in front of the vehicle to be able to, dodge that obstacle either vertically or decide to go around that target. So I'm going to move on to echo sounders. So our company manufactures two types of echo sounders, single beam and multi-beam. Pretty simple image here I just grabbed off the internet to depict the differences between the two. And you have the single beam is clearly just one beam that sends a signal down to the seabed and gets a depth reading and creates a digital terrain map based on basically where it's the vessel is driven, and provides a single line of depth charting. And then on the right-hand side, you can see the example of how multi-beam images. So you have a wide swath of up to 170 degrees. So you have 1,024 beams in that field of view, generating a much more detailed map and full coverage of the seabed. So you can image larger structures. So I'll show you some examples of both single beam and multi-beam data. The single beam systems and the multi-beam systems do need a GPS heading, pitch, and roll sensors to compensate for those position changes, and to be able to put the points, the 3D points, in the correct position and depth for the area of interest. And a single beam data set, this is the real-time feedback that you would get from a single beam. You can see basically this is a histogram. So if you were driving on a vessel, this would be scrolling through and giving you that single depth reading that you can see in the right-hand column. The nice thing about our systems is we're able to provide very, very clean and accurate data. And you can see in this example, there's lots of noise introduced on the acoustic side from the seagrass that's in this area. And our bottom detection capabilities gives us a really clean and accurate depth of the actual seabed, and not taking into account any seagrass, but we do still image the seagrass. And then here's a single beam digital terrain map of an area. So a lot of cases, you don't need the accuracy and full coverage of a multi-beam system, and a single beam does the job for the specifications of the project. So it all depends on what the requirements are and what kind of detail you're looking to get out of a survey. So this is a good example. You can see in the green areas, and the yellow is the shallower water. And then as you get into the blues and purple, you have the deeper water on the depth chart here. And these color maps are all controllable, and you can adjust them to be any kind of scale, especially if you have a much larger depth changes, down to the hundreds of meters. You can change this to have a much broader color scale. It's user preference. Now then we go to from single beam to multi-beam, and as you can see, the detail on complex structures you can get from a multi-beam system is significantly better than a single beam. But like I said, sometimes it's not required for specific projects. But this is an example of a shipwreck and being imaged by a multi-beam. On the left-hand side, you have your bathymetry data, the 3D point cloud data, and then on the right-hand side, you have the just the intensity backscatter data that we're getting from the sonar. And this is the basic user interface. So you have all your controls down on the bottom here, controlling your power, gains, and pulse width, and your range settings there as well. So a simple user face. And I've got, let's see if I can go to the next video. It's a little video of kind of depicting how a vessel flies, drives through an area. And this is the image that you would get real time. So you can see the data being displayed as the vessel goes through in the data collection software real time. Play that again. Yeah, so the vessel is, as I mentioned, integrated with a motion sensor, position, heading, pitch and roll motion sensor, and a GPS system. We typically, on hydrographic surveyor projects, we would use RTK corrections, so we're down to a few centimeters of data that's of GPS accuracy, so we have the most accurate positioning data available. So I'll move on to a different type of multibeam, and that is one that's used for a side scan sonar gap filling capability. So a typical side scan sonar has a blank nadir in the center of the data that's collected. And now, for example, on this AUV that our sister company Teledyne Gavia manufactures, the imaging group partnered with them to use the Blueview brand multi-beam profiling sonar to manufacture a gap fill sonar that does twofold of data collection. One is to fill the intensity backscatter data from the side scan. And then on the right-hand side, you can see we actually collect point cloud bathymetry data from that system as well. And let's see, got a video example of that as well. So this is the traditional way a side scan sonar survey would be, data set would be collected. You have the blank space in the center, and typically vessel or AUV would have to do 200% coverage of an area being surveyed to fill that space in. And with the gap fill sonar in place, it basically fills that space, and it reduces that or removes that requirement to have 200% coverage. So you can either improve your survey efficiency for the specific project, or increase the amount of time the AUV can dive, since they don't have to do 200% coverage. So you can survey a larger area, or even reduce the time it takes to survey a specific area. And this is an example of data that was collected from the pipeline inspection. So the data on an AUV. So the AUV does the full survey and inspection, and then the data comes back, or the vehicle comes back and is downloaded and then post-processed using the Blueview user interface. And then you generate your backscatter intensity and marry it with the side scan sonar data, as well as the bathymetry data that's generated from the sonar. The nice thing, or one capability that is could be a neat function in pipeline example, is if you're surveying a pipeline, you typically have an idea of position where that pipeline is before before the survey starts. So you input those coordinates into the plan, the mission of the AUV, and you can utilize the sonar imagery to correct the positioning of where the AUV is doing the survey. So if the pipeline has moved off course by 1 or 2 meters, just from natural seabed ebb and flow, the AUV could track onto the pipeline using the sonar imagery and adjust the survey line based on the actual pipeline, because that's the real interest is to get the condition survey of the pipeline itself. So one neat way to be able to utilize the sonar as a navigation and survey aid for positioning. And just another image example of some nice, really high resolution data from that sonar on a Gavia AUV. So this is a unique sonar that I mentioned in the beginning that provides both 2D real-time imaging as well as 3D forward-looking bathymetry. So we have the 635 kilohertz receiver in the center, and the projector. Can you hear me okay?
Seem to be cutting out just a little bit. You were fine at the beginning, so I'm not sure if you moved your microphone or maybe an internet type issue.
Yeah, let me get a little closer to the microphone. Is that better?
That is sounding better.
Okay, I'll try to stay close to my microphone. Sorry about that. So the system has a single projector on the top that provides 200 kilohertz projector and 635 kilohertz. And the 635 kilohertz is for the 2D the 2D receiver array, and there's actually three 200 kilohertz receivers, and through some complex calculations and measurements from between when the three 200 kilohertz receiver arrays actually get their return from each individual ping. There's some complex math that is above my head that basically calculates and generates the 3D point cloud forward-looking bathymetry using this one system. So I have some data examples of this as well. So here on the bottom right, you can see the 2D sonar wedge, and that has a max range set to, in this example, of 120 meters. And you can see at about 75 meters, this zoomed in section, during the data collection, we introduced this tripod sonar target just to have something that's, I guess, identifiable by somebody who's not used to seeing sonar imagery. And you can see out at 75 meters away from the sonar, we're getting very good resolution of that target. And at the top here, this is one cast that this is actually collected from a surface vessel, but this sonar was basically designed to be installed on an unmanned AUV. So an AUV or a UUV are the typical customers for this specific sonar. So you provide the forward-looking navigation aid with the real-time 2D, and then the forward-looking bathymetry map as well. And what that does is it provides those two capabilities in one sonar. So we're reducing the amount of equipment, multiple sensors, that would need to go onto the AUV to collect two separate types of data sets. So that's kind of a unique feature and capability with this system. I've got a video again. So this is the video of the 2D data that's that's being collected in this one single pass. I believe the max range is out to about 100 meters on this, and the shipwreck itself, I believe, is about 70 meters long. And then you can see in the picture that's a U.S. football field scale there, so you can see the swath that you can get of coverage. So and that's going to be dependent on your vertical height off of the seabed as well. And this slide is actually out of order here, but I wanted to have this displayed to show an example of the multibeam data in a mine countermeasures test site. So this is actually the multibeam, not the forward-looking sonar. This is the downward-facing multibeam survey grade system. So they actually did a full survey of this site, and with the Danish Navy, and you can see clearly there's the introduced mines that they place on the seabed come in very clear in these water depths. So we have between 17 and 22 meters of water depth. We're able to image very clearly these targets of interest that would be called. And one sonar that is also very unique that I didn't have on the original overview slide is a tunnel profiling sonar. So this is manufactured to be able to be installed on the smaller ROVs or vehicles that do inspections for water supply tunnels, typically, or even hydroelectric dams that have big tunnels in them. And the system provides a full 360-degree multi-beam profiling system. So it's covering a full 360 while flying through these tunnels, and gives you a full 3D image, as you can see in these pictures here. So it's a very unique system. We've only manufactured and sold a few of them around the world because it is a very niche market to be inspecting tunnels in this manner. There's other sonars that have the capability to image this way, but instead of a full 360 real time, the competition is basically a single beam that is rotated around. So it's if the same data would look like a corkscrew with a single beam going through this data, so basically getting a single profile line as you go through this tunnel. So much more coverage and much more resolution capability. So that's the end of my presentation. A couple image examples of some projects that I've been involved with over the years here. I'll just open it up to any questions and go from there.
I got a question, John. How do you tie this down to the Earth? So we go through and we use our multi-beam sonar, and we image a swath of the ocean or a block of the ocean. How do we tie it back to positioning data?
Yeah, that's a good question. So I'll go back to this multi-beam slide, this one here. So we have for a multi-beam or a single beam, we have the on the vessel, we have a motion sensor, so a heading, pitch, and roll is added onto the vessel, and as well as the GPS. So the data collection software is there's multiple software packages on the market, but basically all that ties into the data collection software, and we compensate for any of the motion and position changes real time, and then we create that 3D map that you see that's being generated.
Well, I guess to be a little more specific, how do we do that when we're talking AUVs that are under the surface that may not have access to a direct GPS data of the vessel itself?
Got it. Yeah, so that's a good question. So you would still need all those same sensors that I just mentioned, but typically AUVs and other underwater autonomous vehicles would have an INS, an inertial navigation system, so that instead of relying on GPS signal, once the vehicle goes below the water, you utilize the vessel's inertial motion to compensate for changes. And there's a variety of different quality systems on the market. Obviously, the more expensive, the higher quality, and the less deviation you get over time. The issue is with any INS, over a certain period of time, you'll start to introduce drift into the data. So ideally, you would go dive down. Even with the highest end INSs, you have a certain amount of drift over a certain period of time. So you would dive down, and then ideally you could come back to the surface, regain your GPS positions, and then dive back down and continue the survey. So that's one way to compensate for that drift, is have planned surface GPS signal captures, I guess you could call it.
Gotcha. Thank you.
Yeah.
All right. Do we have any more questions for Mr. Robinson? Robertson, sorry.
Hey, John,
All right,
what
John.
is
Well,
the project? Oh, sorry. Go ahead. Oh, I'll go ahead. Hey, it's Jill. What is the project that's represented in the photo on the left, the lower left on your slide?
Yeah, so this project is actually just a product demonstration. This was in Osaka, Japan, in just a harbor, and the company wanted to inspect the underwater portion of these are, I believe they're called acropods. It's just a water break for this seawall on the backside, you can see. And they're specifically placed to interlock with each other. So the company wanted to do a demonstration and get some example data of how we can help basically during rock placement or even acropod placements.
Thank you. Now, how about the upper right?
So the upper right image is actually a really cool project. I didn't go over this sonar in this presentation, but you can see these dark circles throughout this data set on the outside of the shipwreck. So this is actually a 3D scanning sonar that is mounted on a tripod. The idea is the tripod lands on the seabed, and we mechanically scan the sonar around the area to build up the 3D point cloud. The history behind the vessel itself is it was a steam-powered paddle wheel boat that sank in 1901 on Lake LaBarge on the Yukon River in Canada, and it was a part of the gold rush era that they would bring people up and down the Yukon to deliver them to gold mines and stuff. It sank in about I think it was about 20 feet of water, 25 feet of water, and was very well preserved because it was nice fresh water and very, very cold. So it was a wooden hull.
Thank you.
All right, do we have any more questions for Jon? All right, well, once again, thank you very much, Jon, for coming out. We really, really appreciate you coming to talk to us and telling us all about these different sonar technologies. I know, at least talking to the other folks in here, most of us do not have a maritime background at all. So it's definitely new information for a lot of us. So thank you very much.
Yeah, fantastic. And if there's any more information on a specific type of system or any more information that anybody would like to get, I can absolutely point them in the right direction and help out there. So feel free to reach out. I believe my contact information is on the board out there. So